Alrighty. Okay, so today's do maximum candies allocated to K children. Uh, Apparently um, this was a previously done submission. I did the DSA course on Leetcode, and I think this is part of it. That being the case, though, I'm not sure what the actual answers were, and we'll just do it again. All right, you're given a zero-index integer array of candies. Each element of the array denotes a pile of candies of size candies of I. Okay, so there's some number of candy piles. Okay, you can divide each pile into any number of subpiles, but you cannot merge two piles together. Okay, so you can break apart piles into smaller piles. Okay. You're also given integer k. You should allocate piles to candies. Piles. You should allocate piles of candies to k children such that each child gets the same number of candies. Each child should be allocated candies from only one pile of candies, and some piles of candies may go unused. Okay, return the maximum number of candies each child can get. Alright, so example here, there's 5, 8, 6 candies, you're giving it to 3 children. So you can divide candies, the 8 pile into 5 and 3. And we have now 5 piles of 3. Oh, I see. So this is 5, this is 5, this is 5. We allocate 3 piles of 5 to 3 children. You cannot merge piles. So here, if you have 11 kids and there's only 7 candies, there's no way that you can give each kid a candy. Okay, so you can divide it into any number of subpiles. Maximum number of candies each child can get. So I think when I studied this, you're supposed to divide them. This is kind of like a binary search. You see if allocating P or C candies to each kid is possible. And if it is possible, then you try to allocate more. So you're kind of searching for that best number of candies. And if it's not possible, then you allocate less, and you binary search for the correct candy allocation. And as long as you can determine whether or not the particular candy piles is adequate for K people, then you should be able to do it. So let's do the is possible. Actually, I'll just do a quick explanation. So this is going to be binary search for the optimal number of candies. I'll say that's C given to each of the K children. If possible, C is within range of 0 to what's the most each kid can get? I don't know. Max of the piles. So in theory, let's say each pile is like 100. So each kid can only get one pile, so it's the maximum that. And then if so, when doing search, if C is possible, search in kind of upper half So search in the half that is from C up to your maximum of that range, and then if not possible, I'll say limit next search, in lower half, whatever current range it is. So first we'll just do it if it's possible to allocate C candies. Say C. Let me check if possible to allocate C candies to every kid. So for each pile, we'll count so let's say we'll count the number number given, or piles. It's just ambiguous. We'll say given. So for each pile here, you would, if let's say C is like 2, you're seeing if 2 works. If there's 5 candies in the first pile, then there should be 2 kids that are able to give, they're given 2 candies from it. If it was like 3 is the possible allocation, then there'd only be 1 child that would be given from something with 5, because you can only divide into like 2 and 3. So for each pile and piles, piles and candies, the number given is going to be increased by how many kids can be given from this. So yeah, so this is just a truncated, rounded down division. And then after that, you say if the number given is greater than or equal to k kids, then return true, otherwise return false. So just say return whether or not the number given is greater than or equal to k. Alright, and I'll do a quick check here. I'll print down if it's possible for 3. And see if it just, yeah, I'll just do a quick check here. Return 0. So here it should be possible for 3, given that there's 3 kids. And here there's 11 kids. It's not possible to do 3. Not sure if that's the greatest test. There's 3 kids. Let's say if it's possible to do 6. This should be false on the first test case. So yeah, 6, it should be able to do it like in the first. There should be 2 kids that are able to do it, but not 3. Okay. Alright, so this just gonna be binary search low equals, and this is the binary search for optimal C here. So the low amount would be 0, the high amount would be the number of the maximum number of the candies in the thing. You could even do, like, you could possibly do, as if you do maximum, it actually goes through all the array. I think maybe goes through all the array. Is that any faster or slower than? Yeah, it's fine. And then while low is less than high, then you're going to find the mid index number of candies. Or this is not even index, this is just the mid number of candies. So mid is going to be equal to low plus high divided by 2, truncated, and then if is possible, I'll just say that equals is possible to do this allocation of candies, and if it is possible, then you want to do the higher amount. You want to check for the higher amount. So low equals mid plus 1, else high is equal to mid, and then you just return the ending amount. You turn the ending amount. So you eventually do is possible to the point where it's not possible. So the ending amount here might not be possible. So I think maybe you do low minus 1, or you do just high. I think maybe you just do high. Well, I just do something safe. If is possible at the low amount here, return low, else return low minus 1. Return low minus 1. So in theory, the low and high could be the same amount, like it's 0. So in which case, it's possible to do 0, and you don't want to do 1 less than that. But it could be that the low and high are the same one, but it's too much, or it's the best one. So low starts at 0. Yeah, because you end up being low and high being matching is your stopping of the loop. It could be that it's possible at that stop point or not possible at that stop point. But you don't really check. So here you're checking. All right, I think this is correct. Question is whether or not this is optimal. Is possible for the mid value. Oh, whoops. Actually, what am I doing? I just did the call. Oh, my leaving of my variables and functions are garbage. For every pile in Candies, pile is wrong with this. Pile divided by, oh, C could be 0. Right. Maybe I should start with low of 1. Maybe I should start with low of 1. In which case, if it's not possible to do 1, then it'll just do 0 as the return value. All right. Let's see if I can't improve this. I'm pretty sure this was something similar to what I did in the previous course. Okay. Return the maximum number of candies each child can get. Pretty sure you do binary search. Pretty sure you do binary search. I said binary search for yesterday too, and it ended up being linear. How can you check if for a fixed number of candies, how can you check if each child can get C candies? Yeah, that's this thing. Use binary search to find the maximum C as the answer. Okay, yeah. Okay, so yesterday there was a binary search to linear transformation that or optimization. Is there optimization here that changes from, let's see. Yeah, this looks like there might be a difference between a linear approach versus a log base or n log n approach. So, what to do? What to do? So, if it was something strictly linear, wonder why the hint yesterday said binary search even though it's ended up being linear. So yesterday there was like you process it on the fly and then you lower your values when you see something that's impossible. Something like that. So, or maybe it's just an optimization of how I'm doing this. Is it, so I go from low to high. I go to low to high. I mean, is there a slightly better amount besides the maximum? Maybe if I took the sum of all the candies and divided by the number of kids, that gives a better upper bound. So like, this is kind of the default, but you could maybe say that's not really possible if like there's 100 total candies in all the piles and there's 10 kids, so, or let's say there's 5 kids. So like at most each kid's gonna get 20. So you don't really need to know like the actual biggest pile. So say the sum of the candies divided by the number of kids. Okay. This is coming up. I mean, it's just a marginal improvement. Alright, that was the marginal improvement that changed it. Really? Really? I guess if you start with the actual maximum, like it could take, you're shaving off like 1 or 2 passes, I think. I'm not sure why it'd be that much order of difference. Alright, but in any case,